Welcome to part 3 for section 3. This one's going to be much shorter. It's mostly because of time constraints in the last video that I decided, personal time constraints, that I didn't do this piece, but I probably could have because it's a single page in the textbook, and then the ideas I think are pretty straightforward to illustrate. In this section, Dr. Strong mentions this big idea at the very beginning, matrices of rank 1 specifically. And I call this in my notes a kind of a building block time, because there's a big theorem that will kind of guess, predict, conditional statement that we may think of that could exist and build off on. We'll look at some kind of almost like a case by case, but we won't prove the overall theorem because we need a couple more pieces before we get into that. But just some kind of interesting observations, since we've been talking about vector spaces and column spaces in general. And it's this kind of big idea of every matrix of rank R is the sum of R matrices of rank 1. And just kind of recall from our previous video and kind of conversation that when we talk about rank 1 or we talk about rank R, rank is equivalent to column space, specifically the number of vectors in the column space. The overall dimension of the column space is another way you can think about it. So when we talk about every matrix of rank R, so whatever dimension that column space is in, we can essentially break down that space into the matrix addition of a bunch of rank 1s. In other words, we can break it down into single columns, single linearly independent columns, just to be a little bit more specific, because the column space, as we've talked about, is the number of independent columns, and choosing one to represent that. And so the building block piece here is to focus on this part of the conversation of looking at rank 1 matrices and what are some observations that we can have. And so in the sixth matrix for A, so A6, using the enumeration that the indexing found in the textbook, we have this matrix, this 3x3 matrix. And if we are looking at M dimensional space, so in this case 3-dimensional space, notice that this matrix only has a single linearly independent vector, which going from left to right we'll call 1, 4, 2. Because when I'm looking through this, I can instantly see that this second column is a multiple of the first, and the third column is also a multiple of the first. And so this is kind of the more trivial. It has a 1 along the main diagonal, so that's why I'm going to use this as my column space for this matrix, but you could technically use any of these other ones. But essentially this leads us then to this matrix being of rank 1, its column space of A6 being the vector 1, 4, 2. And what that means is, because there's only one linearly independent vector from what we've been discussing, is that the column space is a line in 3-dimensional space that passes through the origin 0, 0, 0. And the way that we can essentially see that is by multiplying that vector by a constant, C. And he uses, I just want to make sure, A1 being the first column here. If I multiply that first column by a constant, this being the column space in general, this will help see that the line that we are ending up creating is C times 1, 4C, and 2C. So any line that has these components is in the column space of A6. Notice that if C is 0, then it passes through 0, 0, 0. But only the vectors that are of this form fit in that column space. Anything else does not. And so this is one of the conditions, requirements for rank 1, that no matter the dimensional space, we're seeing a single line, and again, that single line must pass through 0, 0, 0. Now, what's interesting, and this is why I wanted to make sure I referred to the idea that when we're looking at the columns, we're talking about M-dimensional space. Because we have 3 columns, but we're focusing in terms of the rows, what if we transpose our thoughts, and instead of looking at M-dimensional space, we look at N-dimensional space? And I start to ask the question, well, we focused on the columns, What about the rows? How many linearly independent rows or how many linearly dependent rows do we have, depending on how we want to look at it, independent versus dependent? Well, if I focus on this first row, we can quickly see that row 2 and row 3 are multiples of this first row. So it turns out that the column space has a rank 1. The row space also has a rank of 1. That these two things are equivalent. There's only one row in this space, and it's the line that passes through 0, 0, 0 and has these major components. We could follow the same format, but in terms of the row. So notice how it's a different line, but it has the same properties or the same features, which is really fascinating and kind of now begs the question, is this always the case? Like if I have a rank 1 column matrix, in terms of its column space, is the row space also always rank 1? And so what Dr. Strong continues to do, and you'll see this in the notes as well, is that we say, all right, well, let's focus on a more basic case and a more generalization of the problem. Maybe this was just unique because we chose these numbers. And so let's take a look at a 2x2 matrix. And let's see if the same property holds. So let's say we have a general matrix A. And again, we know we want a rank 1 column space. So if I call the first column A, B, the second column needs to be a multiple of that vector. So he uses M, so let's call this next entry MA and then MB. Again, we can see that column 2 is a multiple of column 1, so this has a column space of AB, and that has a rank of 1. The question is are the rows dependent or not? And because we only have 2, like, is the second row a multiple of the first row? And if we're kind of asking the question, what do I need to multiply C? Let's just look at the first 2 entries here. What do I need to multiply A by to get to B? Well, I can quickly divide and see that the number is B over A. That's my multiple. And if I go through and I multiply this entry by B over A, that gives me B. If I multiply this entry by B over A, it gives me MB. This is a constant because A and B are numbers. So the second row is a multiple of the first row. The row space of A in A also has a rank of 1. So in the 2x2 case, where we had a column space of rank 1, the row space is also still of rank 1. If we extend this to a 3x3, we're going to see ultimately the same argument and ultimately the same calculations. If we go through and I say, okay, let's do a 3x3 square matrix, A, B, and C this time, and make sure they follow the same thing. Yep. So the next column would be MA, just kind of using the same language, MB, MC. The next column, we could say PA, PB, PC. So all of these, again, are real numbers. Again, we see that this has a rank 1 in terms of its column space. This column is created by multiplying A1 here by M. Column 3 is created by multiplying A1 by P. So I have a rank of 1. Well, if I look at the rows, it's kind of the same argument that we saw a second ago. To get the second row from the first, I'm just multiplying this first row by B over A. To get the third row, I can just multiply the first by C over A, creating all of these entries. The row space, again, has a rank of 1. And so he kind of begs and asks this question of, for any matrix with rank 1, and I guess column space rank of 1, so column rank, just to be more specific, I guess. Got to work more on my terminology, so I apologize. The column rank of 1, then the row rank is 1. And this is the first, he kind of comments on it, it's kind of the first big theorem. If the row rank is 1, then the column rank is 1, and vice versa. So for every matrix, it looks possible that this will happen. He gives the specific conditional statement theorem, essentially. If A has R independent columns, then A has R independent rows. In other words, what if we extended this past rank of 1, and we said, is this true for any rank? Any rank. Because rank is counting independency. What if there were 2 independent columns? Does that mean that the first 2 rows, or at least 2 of the 3 rows in the space, would also be independent and have that same rank? And this is something that we'll investigate later and what we're going to see and kind of pop out in terms of proofs. But this is kind of the central concept around rank of 1 and kind of making some of those observations and kind of creating that building block that will even work up into this idea: can we break a matrix down into rank 1 matrices, specifically the sum of those matrices. And that finishes off 1.3, part of the MBO online class, Mount Vernon Online. Then take a look at the problem set. We have one more lesson set ready to go dealing with matrices. And so when you are ready, feel free to turn to those lessons. We will begin to look at matrix multiplication, which is going to ultimately allow us to then factor. If you think back to our basic algebra, once we know how to bring 2 things together, we'll start to break things apart. We'll do the same thing with matrices. So, thank you.